Okay, this is a short clip about the refraction type questions, including total internal reflection and the critical angle. So the first question involves a semicircular plastic block as shown. We are told that the light passes from air into this block, and you can see it enters in this point here and then travels straight across to the center point, at which point then it will exit the block. It tells us the incident angle is 40 degrees, and notice this is relative to the normal line. That's always the correct angle to choose, the angle between the normal line and the path that the ray takes. And also the refractive index is given as 1.5 for this particular plastic. We're told in question 8 the ray continues into the air, exiting over here, and we're asked to calculate the angle between the normal and the path taken by the ray as it leaves the block. So we're expecting it to do something like this. And so in this case it will bend away from that normal line. This angle should be greater than 40 degrees. And that is because it's leaving a dense medium, a relatively denser medium compared to the air. So we can calculate this, of course, using Snell's law, n1 sine theta 1 equals n2 sine theta 2. The first medium we're going to consider, medium 1, is this plastic block. So we're told the refractive index is 1.5, that's n1. Multiply that by the sine of the angle of incidence, in this case 40 degrees, and that will give us, of course we have to assume that the refractive index of air is 1, so n2 is simply 1, which makes it simply equal to sine theta 2. I mean, you can write down 1 times sine theta 2, but that's not really needed. Okay, so we can crunch the number and simplify this. 1.5 times sine 40, put it into your calculator. And if you did it properly, you should have 0.9464, sorry, 964, isn't it? Oops, take that off. 964, we'll take a couple more figures just to avoid any rounding errors. Okay, so that equals the sine of theta 2. Now if we take the inverse sine of both sides, we can calculate what the size of this theta 2 will be. Theta 2, of course, I'm referring to is this angle here, which we've been asked to calculate. So we take the inverse sine of that number, and if you did this correctly, you should find that your angle is 74.6 degrees. And as expected, that's larger than 40 degrees, so it looks likely to be the correct answer. Okay, question B. Calculate the critical angle of the plastic block. So once again, we can use this Snell's law to do this. But in this case, we're going to replace the term, or a couple of the terms actually. The first term we're going to replace is the incident angle, theta 1. We're going to still write down 1.5 for the plastic block, but now we're trying to calculate theta c, the critical angle. So we'll use that symbol. And of course we still have 1 for the refractive index in here, so it's just 1 times. Now it's sine 90 degrees, because at the critical angle, of course, the light emerges along the boundary 90 degrees from the normal line. And you may know, of course, that sine of 90 degrees is equal to 1. So that simplifies down the entire right-hand side of the equation to just the number 1. So in fact, what we can do now is divide the 1.5 away from this side here, across to this side. So we'll end up with sine theta c equals 1 divided by 1.5. And the next step then is to take the inverse sine of both sides, leaving us theta c equals the inverse sine of that number, which happens to equal 0.6 recurring. If you do that, take the inverse sine of 0.6 recurring in your calculator, you'll get 41.8 degrees for your angle, the critical angle of this plastic block. Okay, question C, what would happen to light rays that were incident at angles greater than that critical angle? Well, we know from previous work, hopefully, that what you get is total internal reflection. In other words, if this is the boundary and this is the normal line, if we are greater than that particular angle, light will come in and simply rebound at the interface. You'll get no light going out into the air at all. And this, of course, is very useful for things like fiber optic cables used in communications and endoscopes used in medicine. Right, last question. Explain why the initial ray that entered the block from the air was not deviated at all as it passed into the plastic block. So we'll just quickly sketch the situation again. Now the initial ray entered from the left-hand side and along that path there. And since this path happens to hit the center point of the semicircular plastic block, we know it must have travelled along the radial line, the radius of that shape, which means via geometry that this incident angle here must have been 90 degrees on both sides. So we can just simply say, since theta 1 equals 90 degrees, no deviation occurs, or no deviation occurred. And that'll do for the answer.